My name's Kevin Harms. As Miriam said, I'm one of the performance engineering team leads. And today I'm going to talk to you about DAOS. DAOS stands for Distributed Asynchronous Object Store. One of the properties of this is that DAOS is not available to probably most of you because it's not part of our current production resources. So Polaris or Theta can't use it. So I'm talking to you about something that's going to be available on Aurora, which hopefully will be in the near future for many of you. And some of you might have access to Sunspot already, and I can say a few words about that at the very end. All right, so I wanted to start by kind of talking about how this might relate to current and present times. Later in the day, some of my colleagues from the research side, Shane and Rob Latham, will be talking about storage, training you on things. All of those things are still relevant for DAOS, even though they're going to be talking to you about using potentially Eagle and Grand. All of the base level concepts will still apply. Whatever you learn will be relevant and just as important. Furthermore, so if we start with Eagle and Grand, those will both be available on Aurora when Aurora goes into production. So if you have code running on Polaris today and it's using Eagle, for example, you can take that exact same thing and run it on Aurora. From a storage perspective, you'll be using the same storage system. So everything you've done to work on that will be directly applicable. If you use local store on Polaris, there's no equivalent to that on Aurora. We don't have local storage unless you use the memory of the node itself. So if you store data in /temp, and then you can do that, but then of course your storage space is very limited to the node's memory. So that might be a use case for if you do use Polaris local memory, you want to port that forward to using DAOS. The next major takeaway for this slide that I want to point out is you can see the performance for Eagle and Grand give you, here we say greater than 650 gigabytes a second. If you look at DAOS, we have greater than 25 terabytes a second. That's somewhat intentional. So it's an order of magnitude more performance, which should be enough motivation for you to get interested and try it out. I would say if you're current today, if you run on whatever system you run on, if the percentage of time spent in I/O is 1%, okay, it probably doesn't matter. You can just use our existing Lustre file systems and not worry. If you spend 5% of your runtime doing I/O, then I would definitely consider it. And if you're greater than 5% or 10%, you should listen in detail to what I'm saying and make careful notes because you'll want to use this on Aurora. There's also a home file system. I didn't mention it here because that's not intended for bulk data storage, but home would be available as it is today. So there would be no changes there. But the performance file system for Aurora is DAOS. So I'll start off and go a little bit about the overall architecture. Again, this is just, you're starting to learn this today so you can apply it hopefully in the future. So in this graphic here, we have this light blue plane. You guys can see the cursor? Yeah, okay. So we have the light blue plane here. This represents the high-speed interconnect. So on Aurora, that's Slingshot, which is the same as Polaris. You can see these red boxes here represent what is the DAOS storage system. And so first thing you can see is that it's directly connected within the storage fabric of Aurora. So we able to leverage the high-speed interconnect to get the most performance. So that's one of the ways we can achieve these very high performance on DAOS is because it's connected to this fabric. You can see here the legacy file systems that we have that are Lustre are on some storage fabric, which is external to Aurora. And so you access them through these yellow boxes. Those are, we refer to as gateway nodes. So in the case of Lustre, your LNet router is running on the gateway nodes, and so that bridges the storage fabric and the high-speed fabric of Aurora and how you can communicate to Lustre. And so Part of this, the external bandwidth is gated by how much external traffic we can send to the storage fabric. I've personally been working on DAOS for almost 10 years, maybe like slightly more than 10 years, but I can firmly say now it's real. So this picture in the top right, that's from the machine room. That's like looking at the back of the storage servers where the networking is entering the server. So yes, it's running. Yes, it's here. It's on the floor. And then below that is just a picture of one of the servers. The next main takeaway here is this down at the bottom where it says 1,024 DAOS servers. So one of the way DAOS achieves performance is by a large amount of parallelism. And so taking advantage of that parallelism will be important. And so, of course, that'll be something you'll learn later on, but again, just pointing that out. The same can be true for other large parallel file systems. You get performance through making sure you have a lot of parallel reads or writes. So to say a little bit more about the network architecture, so in this graphic, we have on the left side, in the case of Aurora, we have 166 compute racks, and each rack is a group. So there's 166 Dragonfly groups, and that's where your compute job would be running on Aurora. We also have some racks then that are dedicated to the storage servers, so we have 8 Dragonfly groups for those. And you can see this purple link represents, down here, there's many more links per arc between these groups than between the storage group, or the compute groups. This allows so that any kind of server-to-server traffic, like if there's rebuilds going on or some kind of data movement happening, that stays within the storage groups and doesn't leak out onto the high-performance network. So DAOS won't, the operation of DAOS won't be interfering with the regular compute traffic. And the service group is where all the gateway nodes are contained. That's where you exit the system. So if you want to put data to Lustre, you're going through the service group. So again, we have these red links that enable data to move between the service group and the storage groups. There's slightly more bandwidth there between those specific groups to make sure that we're not polluting the interconnect fabric. So you won't be competing with storage traffic in your compute job. But of course, and then last thing is every compute group is connected to the storage group. So there's 166 connections into each DAOS group, and each DAOS group is connected to every compute group. All right, so this next part, I'm going to go a little bit about the data model. Again, this is more, you don't have to understand all of these elements in detail. I just want to make people aware, give you some background. So in this outer blue box, you start in DAOS with something called a pool. The pool stands for the physical storage of the system that's allocated. So you allocate some physical storage, and then that's referred to as the pool. Then inside the pool, you can have a container, and that's the level that normally you're going to operate on. So you'll create a container and you'll use that container. And for the most part, your knowledge can stop there. You just have containers. But inside a container, you have objects, and then objects themselves has 2 elements. One's called the D key and one's called the A key. The D key is how data is distributed across all of the storage. So an object can span multiple targets in the system. That's defined by the D key. And then the A key is, your sequential blocks of data that are kept together. And so that's how data is decomposed within the container. You don't need to understand that or know that. I just wanted to make that, just put that out there so if it comes up. But the high-level APIs don't expose objects, D keys, or A keys, so you won't normally be working with that. On the right here, we can just look at this top example, which is inside a container, you can have your classic POSIX namespace that you use. You can have directories, and those directories contain directories, or directories can contain files, exactly as you would use today. So starting to use DAOS is generally straightforward. It's going to look like how you use other parallel file systems. Now you can also have other formats, so you can have a DAOS container that contains a key value store, and so then there's a dedicated key value API. And so in here, it doesn't look like POSIX data. You just have a series of keys and a series of values, and you access it that way. And then, of course, there's other types of formats that are possible. So to say a little bit more about pools, I'll mention this a little bit more, but a project will be assigned a pool that'll be created by the ALCF, and so the system will have, maybe hundreds of these pools, and they're physically allocated storage. So you have some guaranteed resources from that storage that you've been allocated. We'll also allocate you across a majority of the targets, so you have most of the resources. If you have a large project, you can get like a significant amount of the bandwidth. The key elements that probably from a user perspective is the pool has an access control list, and so that controls who can access your pool. So when the ALCF hands you your pool, you would have already like your user group added, but if you wanted to add other people, you could say, hey, can you add these people to my pool? And then they can put in the ACLs for that. We can put some default parameters for your container, so when you create a container, it'll get some properties, which is what we think would be good defaults. So in the pool, you'll interact with minimally. Then containers is where your main interaction comes with DAOS. That's where you're going to start with. And for my first bullet, the main thing if you learn something today is that you can just use one container. So if your project, if it's just say one person, they're organizing all the runs and they're taking care of organizing all the data, you can just make one container, put all your run. You can put 100 million files in there if you want. You can put 100 files, whatever you like, but you only need one container. Now you might want to use more containers if each person wants to work independently and you don't want to share containers, or maybe you're doing 5 sort of independent things, so maybe you'll have 5 containers, one for each of those different things. That's fine. The one thing that's not fine is running sort of a file per process workload, but then making one container for each process. Don't do that. Take all your M&Ms and put them in one container. That's fine. You can still have file per process, just put them all in one container. And then I'll be happy. And as a user, you'll control the configuration of your container, so you have some options. We'll go into more details later. So that's just like a really brief overview of the storage model. There's many more things to learn there, but that's just to give you a flavor. So now, how do you use this? So as I said before, ALCFs would assign you a pool. If you have a large allocation, your pool is going to be distributed across most of the system, but not all of it. So if we have some failures, there'll be targets your project can rebuild onto. And you'll have full rights to manage the pool, but you can always just send a mail like, oh, can we do this? And then the main thing you would do with your pool is just create a container. So the first thing you're going to do, you're going to create a container, and then you can use whatever settings you desire. So on the right side here, I'm mentioning containers. It's a little bit different than your classic storage system. So most storage systems like Eagle or Grand, they're set up with RAID 8+2. So you have 8 chunks of data and 2 parity for those 8 chunks. So you have 10 blocks of data that you can use to compose 8 good amounts of data. Here, you can choose what data protection you would like. So our base target will be 16+2. So to increase the storage efficiency a little bit. So you have 16 chunks of data for 2 parity. But if you're like, this data is like the most valuable data ever, I want full replication, you could turn on full replication in your container. So you can go and select that as the redundancy factor you'd like. You can also, there's some performance tuning with like the EC cell size. Here you would also, if you want to add more people to use your container, you could change your access control list. And another option is, let's say you have data that's you use during the simulation, but it's not used after the simulation. So it's not like a core, it doesn't contain core data that you use for analysis. So once the simulation's done, it's discarded, you never restart from it, or you don't use it. So it's temporary. You could use their no data protection, because you're like, well, if the simulation crashes, I don't need this data anyways, and then get slightly more performance. So you'll have that freedom to configure containers within your pool. Now, I'm gonna then dive into a little bit more details about like how you literally use it. So I wanna go over some of the elements of storage. And so one of the ways you can use DAOS is with Fuse. So if any of you are familiar with Linux, there's something called Fuse, which stands for File System in User Space. It's the main way to use any user space file system. If you've used Linux, you've likely used Fuse at some point. But in this little graphic at the top right, you have an application, and then, let's say you're doing a POSIX read. So POSIX read might be is usually implemented in libc. So libc is going to make a call into the virtual file system. So that's the VFS layer of the kernel. So it'll be a kernel trap. Some operation will go in there, and the VFS will then route that over to the Fuse kernel layer, which will then send the message up to some other component. So there'll be some lookup. Oh, this is for the DAOS Fuse module, and so then it'll pass it off to a component called dfuse here, and dfuse is the Fuse implementation for DAOS, and then that will perform the operation. So in this case, we have Fuse provides very good POSIX compliance because you're as long as the VFS works, then it works exactly the same. It requires no changes to your application because you're just using the same compiled application before. You just run it against dfuse. So that's how dfuse works. It's usually the first easy step to try DAOS out. So I'll talk more about that later, but this is how it works. Another method to use POSIX is through this interception library. So let's say you're running dfuse. You can now link in this interception library using LD preload if you're familiar with that mechanism, but you set an environment variable, you point it to this particular library, and now when you do a POSIX read or a POSIX write, those will be intercepted, and instead of routing into the kernel, these layers of the file system, these will be linked into your application. You'll call these directly, and you'll talk to the storage service directly, never entering the kernel. And so you can get significantly more performance, especially because the VFS Fuse was never designed performance, so it doesn't do large transfers or any other optimizations. That was never its intentional design. So using the intercept library can boost your performance quite a bit. So these are the main ways to use POSIX IO in DAOS. There's also an MPIO driver. So for those of you who maybe know a little bit more about MPICH, there's a layer called Romeo that implements MPI file open, MPI file write, all of the collective versions. All of this is implemented in Romeo. And then Romeo has various different drivers for different file systems. So maybe the most common one is UFS, which just stands for your generic Unix file system. But there's a specific DAOS ADIO driver. And so ideally the system can detect that you're using DAOS, and so then it'll use the DAOS ADIO. But if it doesn't, you can give a hint. So down here, you can prepend this to your file or use some existing environment variable, and that'll say no, whatever file writes I'm doing, please use DAOS. And you'll go directly through the ADIO, so you'll never use any of the kernel, and this will give you sort of idealized performance. All right, so I kind of hinted at how you'll use DAOS, but here's sort of I made this flow chart. I don't know if it's a good idea, but when you come in on Aurora, so maybe a year from now, you're going to be okay, I want to use DAOS. How do I do it? First thing you can do is use Fuse. It doesn't require any knowledge. You don't have to recompile anything. You don't have to understand anything. You just need to know, I need to know what my pool is. I need to create a container, and then I need to mount that container. And so the plan will be that you can just hand a triple to the scheduler and say, this is my pool, this is my container, and please mount it at this location. And so when your application executes, when you do MPI exec, this path will already be mounted for you, and you just access it like you would any other Unix directory. So it's functional. It's also scalable. So horizontally scalable. As you add more nodes, you'll get more performance because each layer will be doing I/O. So from that perspective, you'll get reasonable performance as you scale up. But the efficiency of Fuse on a per node basis is not very good. So if you're trying to get the maximum performance from a single node, that won't happen with Fuse. One of the other parts that it does have that's very workload dependent, whether if it's a good thing or a bad thing, but is it has caching. And so if you choose to turn on caching because you have small IOs or you keep rereading the same elements, caching can be a performance win over these other models that don't currently have caching. So if you have that, Fuse might still be a good choice if you get some win from caching. The next step would be to go and try the intercept library. So you still launch your job in the exact same way that you did with Fuse, but now you just add setting the LD preload statement, and then it will use the bypass for all of the bulk IO operations. And so this should give you a win with getting more efficiency out of each node. So you get significantly more bandwidth from each single node. But there's no change in the metadata performance because all metadata still goes through Fuse today. Perhaps in a year from now, there is a prototype intercept library that intercepts open, close, and the get adders and all those things, but that's still prototype stage. And then the last thing I mentioned was using MPIO. It has the direct ability to talk directly to DAOS. If you have an MPIO code, great. All you need to do is make sure that you're using the ADIO, which is, if it's not auto-detecting it, just adding this DAOS colon prefix to your strings, and then you'll be using DAOS. And that's, again, like idealized performance from MPIO should be good. If you want to do other things, do exist other middlewares that can be tried, but all of those things will then have additional costs to you as a developer of like, how do I figure out how to use these? So these first three on the right are a good place to start with. And don't require any fundamental changes to your code today. All right, and so I'll end with, for those of you who have access to Sunspot today, because if you're part of ECP or ESP for Aurora, we do have DAOS running on Sunspot. So we have 20 node system, it's running today. We don't default allocate any pools or containers, but if you would like one, like you're like, oh, I'm testing, I want to try Sunspot, just send a mail to support. We'll create a pool for you. And if you need help creating containers, or I can point you to some documentation how to use it, you can create the container and then start testing on Sunspot. So that's my extremely brief overview of DAOS. Is there any questions? I know it's in the future for most of you, so you won't be trying it out today likely. Yes. Okay. Yeah, so the question was, how much overhead is in using data, how much gets inflated? So that's very specific to how your workload. Let's say you write a gigabyte. If you do a single write of 1 gigabyte, you'll have very low overhead because you just have one extent, which is 1 gigabyte long. If you write that gigabyte as millions of 100-byte writes or tens of millions, then you'll have very high overhead because each of these writes will be a single extent. At least temporarily, there's an aggregation engine that will then come in the background and be like, oh, all of these extents are contiguous, let's compress them together. So that does happen in the background. But if you write a very let's say difficult workload, which is a lot of holes in your application, so you have all these extents that are non-contiguous, then you'll get a little bit more overhead because all of these extents are tracked.
We have another question here.
Okay.
Thank you so much for the presentation.
Okay.
I'm not expert in parallel file systems, but something that I'm wondering is that what is the advantage of using block storage in place of object storage? Sorry, object storage in place of block storage.
Yeah.
What is the traditional approach?
So one of the things that sort of as a community, one of the largest blockers to performance in parallel file systems is the need to have strict POSIX compliance. So if I write something like the last writer should win, or after all of these things, I should have a coherent set. To do that, you have to have distributed locks, and that just destroys your scalability. So in the case of object storage, you don't have any POSIX strict compliance. And so in the case of DAOS, one thing that you might be lacking is if you count on some very strict compliance corner case for your application to run right, it won't, because the object storage doesn't enforce those things. Now, many things still will work, and most application or HPC applications don't count on those things, right? They do all the coordination within the application and synchronize from there. And so don't count on the file system to provide them those semantics. So because of that, the object storage should be able to scale much better, which it does. We'll hopefully see that in Aurora. But the block storage is still there because, you know, people like their legacy file systems, they want all their strict POSIX capabilities. No one wants to change a 30-year-old, you know, IO code.
So the lesson is that we are trying to migrate the complexity from the system to the application, right? In order to get some performance.
Right, so at the application level, you're likely doing all the coordination, and you don't need help from the file system. All you need the file system to do is accept the data that you put in and be able to give it back to you when you want it. And so hopefully DAOS will be more efficient at that than traditional parallel file systems.
Thank you so much.
Any other questions? Okay, so let's thank Kevin for it very informative.
Thank you.